welcome to the course Advanced Reaction Engineering. So, in this course we are discussing non-ideal flow, that is the dispersion model. So, in our previous class we already have discussed about the dispersion model. So, we will also discuss that, and once dispersion models is over, then 2 parameter models that we will discuss. So, in our previous class we already have discussed that if there is a flow inside of a reactors or a tubes. So, when reactants or tracer any components, when it is passing from one point to the another point inside of the reactors. So, with the convective flow, so there is a diffusion is there of that molecules. So, based on that assumption, so this model has been developed, and for that dimensionless second order differential equations we have developed, and for that to solve that equations we have considered 2 boundary conditions. One is closed vessel boundary conditions, and another one is the open vessel boundary conditions. So, closed boundary vessel conditions that was considered for that case at z equals to 0 and z equals to L. So, z equals to 0, this was the Dankert boundary conditions that was developed, and at z equals to L this boundary conditions was developed. So, for closed vessel condition, and once we have converted that into dimensionless forms. So, at lambda equals to 0 dimensionless length, and when dimensionless concentrations psi equals to Ct by C naught 0 or Ca by C naught 0 C naught. So, in that case when lambda equals to 0, this is the boundary conditions, and at lambda equals to 1 boundary condition is this. So, these boundary conditions we have, and these are differential equations for tracer test we have developed. So, these equations we have not solved yet, but there is a correlations for this particular closed boundary condition tracer test. So, for this space time equals to mean time in this case, and variance sigma square and mean times they are related like this, and there is one correlations I said in our last class also. Using these correlations and tracer test, so we can find out these two, and then these two we can substitute here. So, we will get Peclet number, and then Peclet numbers we can use to solve these equations numerically. So, numerically if we solve these equations, what would be the results? That means here solving these equations is dimensionless concentrations that we want to get, these concentrations we want to get. So, the results we have discussed with respect to the dimensionless concentrations and dimensionless times. So, when dispersions number or Peclet numbers, inverse of Peclet number or dispersion numbers, how they are related. So, that we have discussed. So, when this equals to dispersion number equals to 0, then the reactor should behave as a plug flow reactor, means there is no dispersion. So, when dispersion is extreme means infinite, so then it is behave like a mixed flow reactors, and in betweens. So, this curve or figures we have discussed in your last class. So, now open vessel boundary conditions that we will discuss. In open boundary conditions, this is the at z equals to 0, at z equals to L. So, here dispersion is there, here dispersion is there, here is also dispersion is there, and for open boundary conditions at z equals to 0, molar flow rates at point, this particular points if we consider. So, here 0 minus, here is 0 plus. So, both the places there is a diffusion or dispersion is there, dA greater than 0. So, we have to consider, therefore, the molar flow rates equals to left hand side is this, right hand side is this. So, after that, so if you simplify these equations, then Ct 0 minus t at time t equals to Ct 0 plus at t, that would come. Okay. So, similarly, at z equals to L, there also dispersions is also present at this particular points. So, there also similar correlations we can develop, and we can set the concentration of the tracer at that particular point Ct L minus t, Ct L plus t. So, this at exit condition. So, these are the boundary condition for open vessel, and we have these equations we have to solve considering these boundary conditions. So, if we consider for a long tube, so where the Peclet numbers is greater than hundreds. So, in that particular case, and using this boundary condition 1 and 2 and solving equation 3. So, then we can get these equations. Okay. So, this is the dimensionless concentrations you can say. So, theta psi 1 theta Ct at L T Ct 0 at the exit of the reactor, that there's this particular concentrations means at this particular z equals to 0 to z equals to L. So, hence this way tracer is coming. So, at this particular point, so the concentration means exit concentration is required to find out the conversion. So, therefore, dimensionless concentrations equals to this. So, in these equations we know dimensionless theta that we know, or we can evaluate easily. So, dimensionless theta I think we have discussed, that is the time actually. So, that we can T by tau. So, dimensionless theta Peclet number, reactor Peclet number, and these are the things, and Ct 0 that we need. So, these are the right hand side we have to put, and Peclet numbers how we can find out, and for that we need a correlations. So, from the tracer test we can find out mean times. So, that is Tms that we can find out if space time is available, means if space time is known. So, volume and volumetric flow rate is known, then space time is known. So, mean times from the tracer test we can find out, we can put both, then Peclet number we can find out. This type of correlations has been developed. So, directly we are using that, and Peclet numbers we can put it here, and then dimensionless concentrations or Ct at the exit that we can find out. Okay. So, here's in another case or conditions when Tm greater than tau, means Tm, that is here we will evaluate Tm. So, Tm value sometimes Tm, that is the mean times, and tau is the space as time. So, let us say this and this, it usually like this. If there is non-ideality is there, sometimes due to the diffusions what would happen, Tms may be 10.5, tau equals to 10. So, slightly higher mean times. So, that is due to the dispersion. If dispersion does exit, few molecules move faster. So, mean times or non-ideality due to the non-ideality, maybe due to the non-ideality the space times would be higher, okay, or due to the dispersions. Okay. So, in that case also these correlations is there, these correlations we can use, means another correlations when space time is unknown. So, in that case these correlations we can use, and we can find out means Peclet numbers, and that Peclet number we can use that equations 3 that we have developed to solve that dimensionless concentrations. Okay. So, now means for open vessel boundary conditions we have used to find out these dimensionless concentrations. Okay. So, now we going for we are discussing for flow, dispersions and reaction systems. So, when reaction system means now we have discussed for tracer test, and in that case the dimensionless concentrations we have find out, Peclet number is there, and Peclet numbers we can find out and from the tracer test, and that we can use to solve the concentrations. Okay. So, now if reaction system is there, so this type of material balance equations or mole balance equations we have developed, that already have discussed, and after that this type of equations we have developed for reactions. Okay. So, after that we developed these dimensionless forms of second order differential equations for reactions and dispersions is there. So, when flow, dispersion and reaction is there, for when flow, dispersion and reaction is there, so then we have to consider Ca and Ca naught instead of Ct and Ct 0 that we have used for tracer. So, now we have to use this way, and for the reactions we are considering. So, everything has come in terms of component A. Okay. So, now these dimensionless equations we have developed in your last class also we have discussed. So, here this is called Damkolen numbers and this is Peclet numbers, or 1 by P r equals to vessel dispersion number we can say, and that we already have discussed. So, now closed boundary conditions, the boundary conditions also we have developed at lambda equals to 0 and lambda equals to 1. So, lambda equals to 0 is here and lambda equals to 1, that is here. So, these are the two boundary conditions we have developed in our last class we have discussed, and these are the equations we have. So, one using these two boundary conditions and using these equations for the reactions, if we solve this, so then the dimensionless concentration that would comes, that is this, okay. These equations would come. So, these equations dimensionless concentrations when reactions is there, flow is there and dispersions is there. So, these equations we can use, and open up closed boundary conditions we have to use to solve these equations. So, then these analytical solutions we can get. So, here in these equations we can write this way also in terms of, here we need Peclet number q. What is q? Q is this some constant. So, Peclet numbers from the tracer test we have to find out, we have to put here, and then we can find out either exit concentration at L or conversions we can predict, okay, using this dispersion model. Okay. So, I think this dispersion models is clear to everyone, and it is clear by means we have developed second order ordinary differential equation for tracer test when there is no reactions. In that case, the dimensionless second order differential equations we have used, and that was solved using boundary conditions, and open and closed both the boundary conditions we have used. When reactions is there, so then closed boundary we are considering, and this type of second order differential equation was there, and that equations we are using to solve these equations, and these dimensionless concentrations we are getting. Once we know the tracer test Peclet numbers we know, that we substitute here. So, then Damkolen number also is there. So, that we have to substitute, then easily we can predict what would be the concentrations or conversions considering these models. Okay. So, now we will discuss two parameters models. So, earlier one was the Tang in series models we have discussed, one parameter models, dispersions models, dispersion numbers we have find out. Now, two parameters models, here two parameters are there, means whenever we consider any reactor. So, there are bypassing of the streams is there and dead volume is there. So, these are the two things we have to considering, and based on that we have a real reactors and we have a model reactor, that is the ideal reactor. So, the equations we will develop that will be considered as an ideal, and up to what extent our reactors and behaving or closing that to that. So, that we will discuss by considering two parameters models. Okay. So, in real systems, let us say this is a packed bed reactors and this is model system. So, in the packed bed reactors usually I said dead volume is there inside of that space, means where the catalyst is present. Some molecules when it is entering here remains for longer period of times, and few molecules through the channels leaving out before the pending longer period of times or the space time. So, channeling is there. So, therefore, this reactor systems we can consider as a real systems, and model systems we have considered here. The one reactors was considered, and with that a bypass stream is also there. So, here reactant molecules will be fed here, it would pass through reactors and then it would move here, and here without reacting a part of volumetric flow rates, that is VB, that would mixed up with the exit stream of here. Okay. So, then we will get the exit or outlet the reactant molecules after conversions will get. So, this is your model system. So, now two things I said, there is one bypass volumes. See here V is the real reactor volumes, and if real reactor volumes we are divided in system volumes and dead volume. So, Vs, this is the system volume that in the systems or reactors presents within that volumes the elements means reactants, reactions, everything is going on there, and Vd that we are assuming that is the dead volume. So, that is remain inert. So, inside of the reactors, that does not means in that particular volumes reactant molecules remain, does not take part in the reactions basically. So, this way we are considering, and volumetric flow rate I said it is divided into Vs and Vb. So, this is small v naught, that is equals to bypass volumetric flow rate, and systems, through systems it is going, therefore, it is system volumetric flow rate. So, this way you are dividing. So, these are the things you have to find out. So, okay. So, in the 2 parameter models or 2 adjustable parameter models, so volume of the exchange reactors and exchange flow rates, and tracer test can be used to determine the RTD, and which can be used in a similar manner to determine the suitability of the model and the value of its parameters. Also, the theoretical prediction of the tracer test in the chosen model systems which compares with the tracer's measurements from the real reactors. The parameters in the model as chosen to obtain the closest possible agreement between the model and the experiment. So, this part is very important, means the parameters through these models we will develop. So, that would be such that means the experimental observations and model observation that should match. Okay. So, otherwise that model would not be valid, and then another models we have to choose to validate our means reactors, whether up to what extent it is suitability is there or up to what extent it is ideal. So, in real CSTRs I already have discussed this. So, I am not going to discuss this. So, let us say directly I will come to the model systems. So, in these systems we are considering, let us see reactions A is going to be first order reactions we are considering. So, in these models what we are going to do, we are going to find out the conversions, means whatever the models or model equations we will develop. Once we know the models equations, tracer experiment or tracer test. So, based on that we can theoretically predict the conversions or exit concentrations, that is our objective. Therefore, using these models we will develop some equations, okay, to find out X or exit conversions, or ideally what should be that. So, in the model reactors, this is our model systems. So, here Ca naught is the initial concentrations, and this here is junction 1, here is the junction 2. Okay. So, this junction 2 and this is junction 1. So, here the feed volumetric flow rate, that is split up into Vs and Vb. So, one volumetric feed is coming this way without reacting or passing through the reactor. Once it pass through the reactors, then only these reactions will take place. If it does not pass through these reactors, then there would be no reactions, and with that reactors total volume I said V, system volume is Vs, that is, and Vd is the dead volume. So, we are also considering Vd amount of volume that does not take part or remain as a dead volume. So, here dead volume is shown here, and few stream is, that is bypassing. So, that we are considering here, this stream is bypassing. So, the same things we are models as this way we are representing. So, now Ca naught is here. So, when reactant molecules pass through these reactors after reactions, so the converted streams having the concentration Cas and bypass stream has a concentration C naught, that would be mixed up here, and then we will get Ca. So, Ca is the exit concentrations at here, and Ca is the exit concentration of the reactors, that would be mixed up with this, and then finally we will get this, and based on that we have to find out conversions. Okay. So, now here Vb plus Vs sum of here, and then we will get V naught here. Okay. So, now first material balance we have to do at the junction 2 at point 2 at this particular points, input equals to outputs. Okay. So, input is Ca naught into Vb, Ca naught into Vb, and Cas into Vs. So, that would be left hand side equals to Ca, Ca into this is Ca into Vb plus Vs. Okay. So, this is in, this is in, this is out. So, at these junctions we are doing the material balance. So, this would be equations 1 we can get from balancing material balancing at junction 2. So, concentrations of A leaving the reactors, that would be Ca, C is the concentration leaving. So, rearranging these equations we can get this, or rearranging so we can get this. Okay. So, now we are considering alpha and beta, two parameters we are considering. So, alpha equals to Vs by V. Vs I said system volume, so the actual volume is V. Okay. So, this is the actual volumes of the reactor considering dead volume. So, alpha equals to Vs by V and beta equals to Vb by V naught, Vb by V naught. So, that is the volumetric flow rate ratio, and this is system volume by total volume. And now, these equations, this Ca whatever, that is we have to express in terms of alpha and beta. Okay. So, here equation 2 we are getting means only beta alpha is not possible, only in terms of beta we are expressing. Equation 1 these equations we are expressing in terms of beta. Okay. So, now mole balance on Vs. So, here we have to do the mole balance. So, in the systems or in the reactors there is a reactions, in here A is going to be, reactions would be there. So, let us say R A, that is equals to minus K into C A S. Okay. So, here see, this is the inlet Vs into C A naught, output equals to Vs into here is also Vs into Cas, this is rate minus Kas into Vs. Okay. Rate of disappearance or rate of generations, and this is accumulation part is 0 at steady state. So, now these equations from the reactors and these equations if we rearrange and express in terms of alpha and beta. Alpha and beta I said this is alpha and beta in terms of volume and volumetric flow rate. So, then we are expressing these equations in terms of this Cas equals to this, alpha and beta expressing in terms of this. If we means simplify these equations or express this equation in terms of alpha and beta, it would be this. So, now here we are getting Cs from this equation 3, and say here equation 2 we have obtained. So, here Ca is there, that Cs from 3 we have to substitute here from equation 3. Equation 3 we have obtained Cas equals to left hand side, right hand side in terms of alpha and beta. So, these equations we are substituting there. Once we substitute there, so here this is the effluent concentration Ca, in the left hand side the Ca by Ca naught equals to 1 minus x, that is beta plus in terms of alpha and beta. So, equation 4 has developed. So, by model from our model systems whatever we have considered. So, the final concentration, that is the effluent concentrations, that is the Ca that we are getting here, Ca equals to C naught into 1 minus x, that is in terms of beta and alpha we are getting this. So, here if you know beta alpha value that we can substitute here. So, from here alpha and beta we will get, from we have to conduct the tracer test. So, just we have discussed we have to conduct the tracer test. Once we do the tracer test, then alpha and beta value we can find out, that we can substitute here. Okay. And tau already we know, volume by volumetric flow rate, and or Vs by V capital S by Vs, and K reaction rate constant, that is known for a particular reaction. So, then easily, and Ca naught is also known, that is also known. So, then Ca easily we can find out. Once we know the Ca value, so then Ca naught is known, then conversions easily we can find out. Okay. So, I think it is clear. So, 2 parameters models means how you have developed these models. Okay. So, in these models 2 different parameters. In the next class we will discuss one numerical example. So, means once we know the alpha and beta value, means let us say alpha value let us say 0.7, beta value 0.2 for a particular reactions by considering tracer test. Means here in these reactions, here we have considered reactions, and in this model systems we are considering these reactions. So, for that in terms of this means in terms of reactant concentrations, these equations or model equations we have developed in terms of alpha and beta. So, similar means these model equations or model systems we have to consider, and there's only instead of C naught. So, this is our reactor system. So, instead of treasure CT0 or treasures that we have to pass. So, once treasure will pass, so it would pass through the bypass lines and VS systems B, VS, CAS, CA naught, CT naught, CTS, CT0, CT will get. So, at different time CT we can measure with the help of treasure test. So, once we know the treasure test and so we have developed that formula or equations using 2 parameters models. So, okay, that we will discuss. Okay. So, that models we have to means that equations we have to develop, and there's using these systems alpha and beta easily we can find out, and that we can substitute here. Okay. So, today is up to this I think. So, I think 2 parameter model. So, up to this we have discussed. Okay. So, thank you. So, today is up to this.